Welcome to the 49th QChem webinar. I'm Dr. Huang Liu, research scientist here at QChem Pleasanton. Today, I have the pleasure to introduce Usha Karan at The Ohio State University. She'll be giving a talk on Ab-Initio Frenkel Davydov Exciton model. Usha completed her bachelor degree in chemistry from Harvard University in 2014 and master degree from Indian Institute of Technology, Madras in 2016. He is currently a student in Professor First Group at The Ohio State University and focus on excited state processes in extended systems. Now I'm gonna turn this over to our speaker.
Okay, hello everyone, thank you for joining. I'm Bushra Alam, a PhD student in the research group of Professor John Herbert at The Ohio State University. And in today's webinar, we are going to look at the Ab-Initio Frenkel Davydov Exciton model. So as this title tells you, it is a tool to investigate collective excitations in extended systems. And I'm going to be telling you the advantages of this method and its utility for studying such excitations and give you some examples of the use of this that we have made in our group. So this is the overview of the talk. I'm going to be telling you a little bit about the theory to help you understand the basis for this method. I'm going to talk a little bit about how the individual matrix elements involved in this for this implementation are calculated and certain features of these calculations which help us to do it for larger systems. I'm going to demonstrate some utilities and then finally we'll talk about job control. And there are several ways in which you can make this calculation amenable for larger systems. I'm going to be able to, I'm going to show you that as well. After we go through that, I'm going to talk a little bit about a study that we did recently in our group of Pentacene, where we use the Ab-Initio Frenkel Davydov Exciton model. Okay. So, so this method is actually based on the molecular exciton model of Frenkel and Davydov. So Frenkel was the person who was the first to describe excitations as linear superpositions of localized excitations, and Davydov went ahead and defined this Hamiltonian for a molecular crystal. And the thing to notice about this Hamiltonian is that there are two parts to it. So this is for a system of n fragments, and if you can see the first summation that shows you the parts of the Hamiltonian which are localized on the individual fragments. And then we have the second part of it which talks about the coupling between those different fragments. And so right away, by seeing this expression, we understand that when using such an exciton model, it's important that you understand how you partition your system and the different features that you want to see arising out of the excitations in those systems. So when the word exciton is used, what it really means here is it talks about excited states that may be delocalized across multiple chromophores, but can still be represented as linear combinations of excitations localized on individual chromophores. And if you are looking at an excitation that is localized on one particular chromophore as opposed to being delocalized across multiple chromophores, that's just going to be a special case of this kind of calculation. Okay, so as an overview, the Ab-Initio Frenkel Davydov Exciton model is a completely ab initio implementation of this kind of molecular exciton model that I just discussed. So here I'm showing you, so the structure you see here is a dimer of Pentacene, and what I'm showing you is the different excited state contributions that one can obtain in describing a particular excited state of the system, or psi exciton. So basically we see, for instance, if you look at the fragment that I'm showing you right here, these are both at the ground state, and there will be fragments where there are localized excitations on individual fragments. There will be fragments where there are cation and anion fragments in order to help you study charge transfer configurations. And also, very importantly, one can also include multi-exciton configurations. And we're going to look at all of these in a bit. But basically, the motivation of this is that you have a wave function, and the point is to be able to describe it and tune it in terms of how you want to describe the individual contributions arising from the fragments. So as I discussed, the Ab-Initio Frenkel Davydov Exciton model helps us to describe collective excitations as linear superpositions of monomer states. So if you look at this expression, psi n is the nth excited state that we're looking at. And if you see here, so we have psi star A, which represents the excited fragment, and then we have a direct product with all other fragments in their ground state. And just to kind of show you what that looks like for a system of, for instance, 3 fragments, this is what you would obtain. You would be describing the excited state wave functions in terms of 3 different basis states where there are excitations localized on individual fragments. And the coefficients before those fragments would determine their contribution to the overall excitation. Okay, so what are these? So when we look at the individual basis states here, the direct product basis states composed of contributions from individual fragments. So let's look at these in a little bit more detail. So this represents a direct product between monomer configuration state functions. So this represents a direct product between configuration state functions obtained from monomers of fragments A, B, and C. So in this case, we specifically see that psi B and psi C correspond to ground state fragments, so those are going to be Slater determinants in this implementation. And psi star A is a singly excited fragment. So the configuration state function for this is described as spin-adapted summation of singly excited determinants. But these are not the only kind of excited state, not the only kind of basis states that you can include in this model. You can also include charge transfer configurations where where you define cations and anions in pairs on different fragments, and the contributions of those can help you study the presence of charge transfer or charge resonance states, as we will see later. And it's important to remember for all of these that the individual configuration state functions are obtained from unrestricted SCF calculations on isolated fragments. Finally, there's another kind of configuration that you can include in this extern model basis, which is the multi-extern configuration. And the multi-extern configuration means that it involves excitations on multiple sides. And if you're and the importance of this is that if you're using a single excitation theory like TDDFT or CIS, then you're never going to be able to include this kind of configuration. So in these multi-extern configurations, we have basis states of this sort, which couple triplet wave functions on 2 different monomers to an overall singlet. And and so there may be different reasons as to why we would want to include such a multi-extern configuration, and in the case of singlet fission specifically, this is quite important, and so the extern model has been used to study singlet fission in both tetracene and pentacene in our group. So now that we've discussed that this is a fragment-based exciton model, and we are able to we're able to customize what kind of fragment basis states we want in our calculation, let's talk a little bit about the computation of Hamiltonian and overlap matrix elements. So the exciton basis states are non-orthogonal. They arise from different calculations on isolated fragments, which means that in order to solve this problem, we need to also calculate the overlap matrix and then solve a generalized eigenvalue problem. So if you look at this expression here, so far I've been using a system of 3 fragments to show you similar expressions, but you could really have a much larger number of fragments, and in every matrix element you're going to this method involves all fragments, and hence the number of terms can quickly grow and become very large. So to minimize the number of terms, the fragment excited states are transformed to a natural transition orbital basis. And what that does is that it does neutral transformations in the occupied and virtual orbitals and transforms them to paired particle hole NTOs. And depending on the occupation number of those NTOs, you can decide how many NTOs you want in your calculation. So basically, what you need to take away from this, from all this information given you, is that the calculation of these matrix elements can be very expensive, but so the original developer of this model has come up with a way of reducing the number of terms in these matrix element computations, and what the user needs to do is define the threshold of how many NTOs to consider, and that is going to be defined as a user-defined fraction of the excitation amplitude, and I'm going to be talking about that in a bit. And there are recommendations for what kind of truncation threshold works for these calculations in the QChem manual. So, as I already discussed, since the direct product basis states involve all fragments, the cost of calculating each matrix element obviously starts scaling with supersystem size, which can become very large. However, exchange interactions are short-range, and so to mitigate the cost of these matrix elements, a charge embedding scheme is used, which differentiates between significant and insignificant interfragment interactions. So what the user needs to do in order to take advantage of this charge embedding scheme is to define a distance threshold from the excited fragments. So basically, if you have an excited fragment A, you define a distance threshold of, say, X angstroms, and all fragments lying within that range of the excited fragments are treated exactly, and this is the key conclusion. And fragments lying beyond this are treated as point charges, which is the region. So the user needs to define a distance threshold, and actually an optimal distance threshold has been found to be 0 angstrom, which basically considers the fragments in the excited fragments involved in the excited region in the QM region and all other fragments in the region, and this is found to be a pretty good approximation. Finally, analytic derivative couplings with the AIFDM have also been implemented. So the derivative couplings describe how nuclear motion can couple adiabatic states. And in order to calculate the derivative couplings, an intermediate quantity that you need are the derivatives of the matrix element in the exciton basis. So these have been implemented, and also the derivatives of the matrix element can also help you to calculate exciton-fermat coupling constants. I will be discussing this if anybody wants to know about this further, but basically, if you want to calculate Holstein or Peier's coupling constants, which are commonly used to describe energy transfer in organic photovoltaic systems, you could do that. And the use of this has been described in a paper that was published by a group on Tetrazine. Okay, so in summary, the AIFDM is very parallelizable. Matrix element and fragment SF calculations can be distributed across processors, and coupled with the charge embedding scheme, it can be used as the excitations in extended molecular aggregates, which is important because typically if you're looking at some of these systems, it is important to have the bulk environment present in your calculation. So as an example, AIFDM was used to study energy transfer in self-assembled nanotubes. These are subunits and a larger unit of a naphthalene diamide nanotube, and the dynamic study really showed that there were edge effects present when you use smaller systems. But if you want to study a larger system that could get rid of these edge effects, the AIFDM is helpful since it is parallelizable. We have also recently studied vertical excitations in Pentacene clusters, and this was interesting because it showed us the impact of the energetics with increasing system size, and also not just the increasing system size, also the fact that the AIFDM can include multi-exciton configurations was especially important for this study. So this is the background theory for this method. Let's talk a little bit about the job control. So to run an AIFDM calculation, you need to set AIFDM set to true. If that's set to true, you're going to get an AIFDM calculation run, the basic one. It's important to specify the number of roots. So the number of roots corresponds to the number of localized excitations, corresponds to the number of localized excited fragment states that you're defining, and if you increase the number of roots, that increases the variation and flexibility. The CIS singlets and triplets keyword is going to help you specify the excited state multiplicity. And generally, when states of a single multiplicity are allowed in one calculation. So if you want to run a calculation where you want to probe both the singlets and triplets, I would suggest running 2 calculations. However, if you want to include the multi-exciton configurations, you need to include both CIS singlets and triplets in your calculation, set them both to true. If you want to go ahead and add additional configurations such as charge transfer states, you need to set AIFDEM states set to true. And if you want multi-exciton configurations, you need to set AIFDEM fish to true. As a reminder again, if you use multi-exciton configurations, you need to set AIFDEM fish to true, and you also need to set CIS triplets and CIS singlets both to true. The AIFDEM NJ threshold helps to control the number of NJs retained. And for organic molecules, 85% has been found to be a good trade-off between timings and accuracy. The AIFDEM embed range specifies the range of Q region for charge embedding. So you have the option of no charge embedding, where your entire system is treated exactly. You can also use an embed range of 0, which only treats excited fragments with QM, or you could specify a distance threshold in Armstrong within which to treat non-excited fragments with QM. If you wanted to compute derivatives, you would need to set state deriv to true, or 1. Along with that, you need to make sure that AIF embed range has been omitted, because currently the calculation of derivatives is not supported along with embedding, and you also need to set sys and roots to 1. So let's look, based on this job control that I've discussed up to now, let's look a little bit at some input and output files. So if you want to run, so this is a calculation of water dimer, and if you want to run an AIFDEM calculation, this is what the input file would look like. So I have defined some fragments. You can define fragments any way you want, as long as covalent bonds are being broken between fragments. So here I've done a singlet calculation. I've set CIS triplets to false. I've set AIFDEM to true with a 100% NTO threshold and an embedding range of 0. So if this is the calculation you do, then this is the output for the water dimer. So the output lists everything very neatly. So it tells you the exciton side basis states included in this job. So this is a ground state basis state, which basically means that all fragments, in this case a dimer, both fragments are in their ground state. We have locally excited basis state, where fragment 1 is in the excited state and fragment 2 is in the ground state, and vice versa. So for this job, since we did not request any additional configurations, this lists the AIFDEM basis. And here we have the AIFDEM overlap and Hamiltonian matrix listed, and then the eigenvalues that you get from your from these, as well as the eigenvectors. And it's useful that these eigenvectors and eigenvalues are ordered according to energy, according to increasing energy. So this is what you obtain for a one-shot calculation. Let's look at a calculation where we have added additional basis states or requested additional basis states. So this is the panel on the left is the first job that I showed you. The panel on the right is one where I have added some keywords. So here I have set AIFDEM CT states to true to include charge transfer configurations. And I have set AIFDEM fish to true to request multi-exciton configurations. And that requires me to set both singlets and triplets to true. Once we do this, if you look at the output file, here's the new exciton basis, and here we see basis states 0, 1, and 2. We are familiar with these already, but we see some additional ones. So in basis state 3, we see, so what this means is that the cationic fragment is the first one, the anionic fragment is the second one. And vice versa. And then the fifth one, we see that this is a coupled triplet state where the triplets are located on fragments 1 and 2. So this is the same system of 2 water molecules, but with additional basis states. And obviously, the size of the basis increases. We have a larger exciton basis. We have a larger overlap matrix and a larger Hamiltonian matrix, and a concomitant number of eigenvalues and eigenvectors. So these are calculations that can run at once, but you may have limitations on your computing resources, or you may just be wanting to calculate a really large set of calculations for a really large system, in which case it is helpful to break your calculation up. So what I mean by breaking the calculation is simply to chunk up your calculation where just a subset of the AIFDM matrices are calculated for each system. Okay, so let me just walk you through the job control for that. So if you decide that you're going to segment up a calculation which requires 10 matrix elements into 2 batches, and you could do that with AIFDM seg-start and AIFDM seg-end, which need to be used together. So these, as is pretty obvious, index the first matrix elements within a segment and the last matrix elements within a segment that you want to calculate. Additionally, if you want to skip the fragment SCF calculations in such a case and not run them every time you're calculating a new chunk of calculations, you could set AIFDM fragment right to true, which computes the fragment calculations only, and this does not compute any matrix elements. And then you repeat the same calculation with AIFDM fragment read set to true. And what that does is now it proceeds to calculating the matrix elements, but it reads the fragment data from that has been written by this job. So in summary, for large calculations, if you want to chunk it up, you need to use AIFDM seg-start and seg-end, and they need to be used together. And you need to make sure that you're calculating all the matrix elements correctly. And if you want to further save time by skipping the SCF calculations and not having to do them every time, you could use fragment write to compute them once, and then fragment read to read that data. And so obviously, if you use fragment read, you need to have done a calculation that said AIFDM fragment write to true before that. Okay, so in order to chunk up your calculations and know the first matrix and the element and the last matrix element within a segment, you need to know the total number of matrix elements. So the way to calculate this is pretty straightforward. So for a system of n fragments, and let's consider system roots to 1, the total number of matrix elements can be determined as follows. So the ground state fragment is always going to give you one basis state, right? Because it's only one unique basis state where all the fragments are in their ground state. And then you can have basis states where each fragment is individually excited, and so the number of singly excited fragments corresponds to n. The number of charge transfer fragments corresponds to n times n minus 1, and the magic stone fragments can be defined this way. So for a general case where the n corresponds to 2, the total number of basis states corresponds to 6. And this also corresponds to the matrix dimension. So total number of matrix elements can be calculated using this, and we find that for a dimer calculation, where you're inverting both charge transfer and multi-extern configurations, you end up with 21 matrix elements. So if you do a one-shot calculation like I just showed you, you don't have to worry about this, but if you want to chunk it up, you have to make sure that you're doing it so that in one calculation, your seg-start goes from 0 to 10, and the second one goes from 10 to 21. So this is a segmented version of the calculation for the water dimer where I showed you where we have requested the additional configurations. And so just to compare what it actually does is it literally breaks up the matrix into smaller segments. So if you have a single calculation here, which is the calculation I showed you in the second step, so we have the overlap matrix. This applies to all other matrices, but I'm showing you the overlap matrix as an example. We find that the entire matrix is being calculated in a single calculation. But if you segment it up into 2 calculations, then if you look closely at, for instance, the second column for ease of analysis, if you add up the second column here for the first calculation with that of the second calculation, you end up with the second column for the supersystem calculation. So when you're segmenting calculation, what you're doing is you're literally saving the matrix elements in different jobs. So the thing is that these are going to be saved in the scratch directory, and so when you break up a calculation, the matrix elements are going to be saved in the scratch directory, and you need to combine them. So the matrices for each job are stored in the file number 4200.org. The overlap and Hamiltonian matrix are stored sequentially, and so you want to remember that each of them has dim square elements, where dim is the AIFDM matrix dimension, which I showed you a few slides back how to calculate. And then once you've pulled all that data, you're going to add up the overlap matrices from all the different calculations and H from all the different calculations to obtain the H dot and the S dot, which correspond to the total Hamiltonian matrix and the total overlap matrix. Now, you need to remember that this is not orthogonalized. So then you need to go in and use canonical or symmetric orthogonalization with the help of the overlap matrix in order to diagonalize it and get your eigenvalues and eigenvectors. All this is done internally in the calculation if you're doing it for a one-shot calculation, but if you want to segment up your calculation, you have to do this yourself. So now that we've talked about the theory of the AIFDM model and sort of the job control, I want to talk to you about a recent study we did using AIFDM. So in this study, we studied charge separation in the low-lying excited states of pentacene. So pentacene is a molecular crystal that I mentioned a little bit earlier. And in the context of certain chemical processes like singlet fission, it is of interest to understand how much of the excited states, low-lying excited states of pentacene have a charge-separated character. So we use AIFDM to study it because A, AIFDM can treat larger systems, and B, it can help us define charge transfer as well as multi-exciton configurations, which help us analyze the eigenvectors in a certain way as I'll show you. So for this calculation, we had several different clusters of pentacene to study the effects of side. So we had pentacene dimer, pentacene tetramers of different configurations, and pentacene hexamer. So let me show you the matrix we obtained for the pentacene dimer, just because this is smaller, but we did the same analysis with the pentacene tetramers and hexamers. So on the left, we see the AIFDM Exciton basis, which I described to you a while back. So we have the ground state basis, we have the locally excited basis, we have the charge transfer-like configurations, and we have the multi-exciton basis state. And the eigenvectors we obtained here are the energy ordered eigenvectors that you obtain at the end of a calculation. And we inspected the coefficients corresponding to the different basis states, and based on the coefficients, we are able to assign characters to these excited states. So, for instance, because eigenvector 2 or excited state 1 basically has a large coefficient corresponding to a charge transfer basis state, we assign this to be a charge transfer excited state normally. And so this is important because even though we're just looking at the coefficients and this is not 100% charge transfer, it still helps to provide a chemically intuitive view if you want to compare excited state 1 versus, for instance, excited state 2, in the sense that excited state 2 has much less charge separation than excited state 1. So one important advantage from the AIFDM is being able to use the exciton basis in order to assign chemical nature to these excited states, which may be relevant to your problem study. So these are the eigenvectors for the dimer in the exciton side basis. Let's look at some of the excitation energies that we obtained for different systems. So on the left, I've shown you the excitation energies obtained for two different configurations of the tetramer. So one was a linear and the other was compact one, and blue squares represent charge transfer states and the orange square represents non-charge transfer states. And by charge transfer and non-charge transfer, I'm referring to the characters we assign using these coefficients. And as you can see, the lower part of the spectrum is pretty much dominated by charge transfer states for both tetramers. And we see these even for the hexamer, as well as the dimer. And we find that the energies of the charge transfer states are more sensitive to the environment compared to the non-charge transfer states. So if you look at what I mean by that is if you look at the excitation energies for these tetramers, we find that for the orange region, which correspond to the non-charge transfer states, there is not a very marked difference based on configuration. But for the charge transfer states, the states corresponding to the compact tetramer consistently lie below those of the linear tetramer. So the AIFDM model helps us to tease out that kind of sensitivity. And here I've listed the excitation energies grouped by the qualitative nature of the excited state. So for instance, I have the dimer energies shown in dark blue, the tetramer energy shown in pink, corresponding to the compact one, the linear tetramer energies in mustard, and then the hexamer energies in green. And if we look at the y-axis, we find that, so what I've done is I've listed the single-excited eigenvectors first, and the multi-exciton, then the eigenvectors having multi-exciton character next, and then the charge transfer, the ones with the charge transfer character. And so we find that in all of the cases, the energies corresponding to the hexamer lie lower, showing us the importance of bulk stabilization for these excited states. And we also find that for the charge transfer states in particular, the stabilization obtained in the hexamer versus the other systems is larger than compared to the for the other systems. So in summary, the AIFDM is a fragment-based exciton model with a customizable exciton basis. This can be tailored to the problem of interest. Extended systems can be investigated for size-dependent trends, like I just showed you with different size clusters, as well as to model bulk environment effects. And adiabatic states can be assigned diabatic labels for ease of analysis. For acknowledgements, I'd like to thank my group and Professor Herbert, and also Dr. Adrian Morrison, who basically developed the whole exciton model that I just discussed with you. And now I'm ready to take any questions.
Thank you, Bersha. It's a thorough and informative talk. First one, in the preparation of basis states, are the polarization effect of the environment taken into account?
So there's no dynamic correlation in the external model that I just discussed. There is some correlation at the CIS level, but no, there is no dynamic correlation currently.
So second question, the method work only for single point calculations, or it can be used for the optimization?
These are for single point calculations.
In the calculation for Pentacene dimer, these states are paired with cis or T.
I missed the last part of the question. So
the basis states are paired with cis or TDDFT.
Could you repeat the whole question again? I think I missed the last part, sorry. So for the basis states for the AIFDM calculation, I got that part, but I didn't understand the second part.
So it's on the same person. The second part of question is, what about the calculation of the matrix elements?
The calculation of the matrix elements. What's the exact question about the calculation of matrix elements? Is it possible for you to type out the message in the chat?
I assume he's asking those the calculations done by cis or the TDDFT.
Oh, it's done with CIS, yes.
So we have a new question. Can someone perform a calculation using the periodic boundary condition?
No. The answer to that is no.
So it's not implemented yet. Okay.
Yeah, it's not implemented yet.
So I actually have a question. So how large is it tested, and how does that perform?
So, so it has been tested quite extensively. So, for clusters of water molecules, which are pretty large, compared to supersystem CIS calculations, the accuracy was within 0.1 to 0.2 eV for the excitation energies. So I would say that it's very accurate.
So correct me if I'm wrong. So I would expect the scaling, the rough power of the number of fragments.
It scales with the number of fragments so the scaling is number of fragments raised to 2 to 4. It depends on the system that you're calculating with. So ON to the fourth is the worst case. It could also be ON twice. And there's also a factor of the total number of fragments squared. So I could show you that. So it's described in the manual as well. So charge embedding the minimal threshold of person algorithm of scales as this. So yeah.
Do you see changes in coupling values with regard to the number of fragments?
I would say that with the number of, if you're changing the number of fragments, then you're changing the number of basis states. So the couplings that you obtain you would get a larger number of couplings. But whether the individual couplings for states that are present in both calculations would change or not, I'm not sure. But you would get a larger number of couplings if you have a large number of fragments, yes.
Is it possible to use the Computation functions to perform this type of calculations with CI?
Currently, no. So these are all based on Hartree-Fock orbitals.
Thanks again, Bertha. It's a really informative talk.
Yeah, no problem.
I'm gonna bring this. I'm gonna bring it to a close here.
Okay.
Thanks, Bertha, again for the speaking and bringing together.
Okay. Yeah, thank you.
I also like to thank our attendees for watching and participating. Video will be posted on YouTube in the next couple of days. If you have questions after this webinar, you can also go to email me or go to the talk.qcan.com. There will be a thread about this webinar, and you can pose your question there.
This concludes our webinar. We also invite you to visit us on Facebook. Thank you for your participation, and see you at the next webinar.